Good evening, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 15th problem from the Project Euler Problem Archive. So this problem asks us to find the number of paths through a square grid, starting at the top left and moving to the bottom right, following the grid lines and only moving down and to the right. Now, some of you might immediately make the connection between this problem and Pascal's triangle. And some of you may conclude shortly thereafter that our answer is just the 21st central binomial coefficient. And so then some of you might open up your calculator and type in 40 factorial divided by 20 factorial squared and come up with this answer. But as satisfying as a 30-second solve may be, it's not much help to those of you who maybe didn't make those connections. And so in this video, we're not going to be doing any such fancy analysis. We're just going to be solving this problem using C and C++ and standard programming techniques. So let's get into it. As usual, we'll copy our template directory to make our problem directory, and we'll open up our main.cpp. Now, there are two techniques that I want to use to solve this problem. The first we've seen in a previous video. The second, I believe, is new to this series. So the first is recursion with memoization. We, in a previous video, used this to solve a problem involving the Hailstone sequence and the Collatz conjecture. And the idea is that we're going to use recursion, that is just a function that calls itself. But then we're also going to use some kind of cache to keep track of our results, so we can avoid recomputing the same results multiple times. So to start with, let's just write the recursive solution. So we're going to have a count routes, and it's going to take a row and column. Let's have some local variables, call it north and west. So one key observation for this problem is that if you go back to our grid here, from a given intersection, say this middle intersection here, the number of routes to that intersection is just going to be the number of routes to the intersection north of it, plus the number of routes to the intersection to the west of it. And that is because the only way to reach that intersection is either from the north or from the west by the rules of the problem. And so we're going to just have these local variables to keep track of the number of routes coming from the north and the number of routes coming from the west. Okay. Let's see. So we can say if row is equal to 0 and column is equal to 0, then return 1. So every recursive function has to have some kind of base case. Because the function calls itself, there has to be some way that it eventually stops calling itself. Otherwise, you end up with this infinite regress. And so for us, our recursion will stop when we reach the top left corner. And we know that there is only one way to reach the top left corner, and that is at the start. We start at the top left corner. And so in that case, we just return 1. Okay, so then we want to say something along the lines of, north is equal to count routes row minus 1 column, and west is equal to count routes row column minus 1. But there's one point of failure here that we have to notice, which is that if row is equal to 0, this will give us a negative number. And so we want to be sure to check to make sure that row is non-zero here and column is non-zero here. And so we might say something like, if row, then we do this. And if column, then we do this. And then we want to be sure if row is 0, for example, we want to have north initialized to 0, and for similar reasons, we want west to be initialized to 0. That is, if we're in the first row, there will be no routes coming from the north, and if we're in the first column, there will be no routes coming from the west. Okay, so then at this point, we can just say return north plus west. And here we want to print out our result, so we'll say let's create a variable up here. We'll say const uint 32t grid size equals 2. Actually, one point of caution / clarification here is that this is a 2 by 2 grid, but there are 3 rows and 3 columns. And so we actually want to say the grid size is 3. So we're going to, in fact, to clarify, let's call this something like numcols. Because size is ambiguous, and I think this will help us keep clear that we mean the number of columns rather than the fact that it is a 2 by 2 grid. Okay, so now we can say, let's see, %u by %u grid has %lu routes. And so that's going to be, numcols minus 1, numcols minus 1, and count routes numcols minus 1, numcols minus 1. And let's also set, again, just to make our code easy to read, we'll say num rows is equal to num columns. Okay, so if we go over here, go to our problem directory, make, solve, 2 by 2 grid has 6 routes, and that matches the test input that they've given us. You can see the 6 routes listed here. So now you might think it's just as easy as going up here, cranking this up to 21, rebuilding, running that, and waiting for, I don't know, the next week, something like that. Not really sure how long it's going to take, but it's going to be a while. And that's because our recursive approach here is actually traversing every possible route, which is fine when we only have 6 routes. But going back to our calculator here, if you have 138 billion routes, that's going to take a little while. And so we need to find a better technique. And I've already mentioned that technique is memoization. So the idea with memoization is that when you have some sort of recursive algorithm like this, as you achieve certain results, then you cache those results so that you don't have to calculate them again. And so we'll just say uint 64t cache, and we'll say num rows, num cols. And because this is a global variable, this will be initialized to all zeros. That won't always work, but in our case, we know that every square is reachable. So if a value in the cache is 0, that means we haven't yet calculated the number of routes to that square. Or excuse me, intersection. Okay, so then we can go down here and say if cache row column, then return cache row column. And then if we have a cache miss, we have to be sure down here to update our cache. And so then we'll just say cache row column equals north plus west. Perhaps we'll make a total, and then we can say that equals total equals there, and then just return total. Yeah, that should be good. Okay, seems like there's been a little bit of a mistake. So let's see if we can identify where the problem was introduced. So most of our logic has remained unchanged. Oh, I expect we probably want to do something like actually I don't think that should change anything. Well, let's check with our 3x3 result again to make sure that might make it easier to debug. No, that still says 6 routes. Okay. Oh, I expect that perhaps somewhere we're using a, yes, we're using 32-bit integers, and so that will be the source of our difficulty. There we go. That looks more like what I'm expecting. Okay, and yes, that matches what we expect. Okay, so that's recursion with memoization. Now, the next technique, which has not come up previously in this series, is dynamic programming. And to some extent, dynamic programming is the same kind of idea as memoization. You're just coming at it from the other end of the problem. And so rather than recursing and keeping track of results as you find them in whatever order you should happen to find them, dynamic programming starts with the results that you know you have and only considers those squares which can be determined based on the squares that you've already considered. So to be a little bit more concrete, if we have a square grid like this, we know that looking at the first row, we can move from left to right, and we can always determine the value in the first row. And then moving to the next row, we know that we can determine the number of routes to the position in the first column because it's just the same as the number of routes to the intersection above it. But then we can determine every other result in that row if we're moving left to right. And that's because we've already calculated all the results for all the previous rows, and we've already calculated all the results for every column in our current row up to our current intersection, and so we know we can determine our result. If that's not entirely clear, maybe just hold on a minute until I write the code, and then that might make it a little bit more concrete. Let's see. So this solution is perfectly fine, so we're not going to delete that. But let's just comment that out. And we'll just put our solution directly into the main function here. Okay, we're probably going to want row and column. We're going to start by saying cache 0, 0 is 1. For the same reasons as before, we up here checked for row and column equal to 0. So we're starting by initializing that. And then we're going to say for column equals 1, column less than grid size plus plus column. And we're just going to say cache 0 column is equal to cache 0 column minus 1. Okay, so now we've initialized the first row. So now let's do all the subsequent rows. So we'll say row equals 1. Row is less than grid size plus plus row. So the first element in each row is going to be determined by the intersection immediately north of it. So we'll just say cache row 0 is equal to cache row minus 1, 0. And then we'll say for column is equal to 1, column is less than grid size plus plus column. And here we can have our usual logic of cache row column is equal to cache row minus 1 column plus cache row column minus 1. Excuse me, this should be 1. And you'll notice at this point, it's guaranteed that both column and row are non-zero, and so this will always be, we don't have to check that we're in the first row or the first column because we handled those separately like this. Okay, and now we can just read directly from the cache. Down here, we'll say cache 2020. That's not a command. All right, we've made a few mistakes. Oh, excuse me. That's right. I renamed this. So this is not grid size. This is num cols. This is num rows. This is num cols. And this should be num rows minus 1, num cols minus 1. And you'll notice that one advantage of generalizing like this is that if I were to change num columns and num rows, this approach would still work as written. Okay, so pulling up our calculator once again, that appears to match. And so our dynamic programming approach works as well. Just to, for completeness sake, let's go back to the archive and verify that our number does indeed match. And you can see here that it does. So that's it for this problem. In the next video, I actually am going to delve into some of that analysis that I breezed through at the beginning of the video. There's actually quite a bit of interesting mathematics there. So if that interests you, then please look forward to that.